We start off with a little bit of review from Algebra 1. We talk about input, output variables, or explanatory response variables. Those are synonymous. Remember that the input variable is the one that is plotted on the horizontal axis. That's the x-axis. It's the one that helps explain another variable, whereas the response variable is plotted on the vertical axis. That's the y-axis, and it's the one that can be explained. So between explanatory variable, input variable, variable on the horizontal axis, a variable that helps explain another variable, make sure you know that those are all synonymous ideas, just as response variable, output variable, vertical axis variable, or one who is explained, that those are synonymous. And the idea being here, we're clearly talking about paired data, specifically paired quantitative data, that can be plotted visually like you would have done back in algebra class, where we can plot these on the x and y axes so that each data point is actually a pair of data points, one with an x value, one with a y value. And the idea that we're trying to get across here is that the x generally helps explain the y. That doesn't mean x causes y. We'll talk about that more later. It's that x helps explain y. So another reminder here, when you have the equation y equals ax plus b, we say that a represents the slope and b represents the y-intercept. Now make sure you understand that the slope is not the first variable listed in the equation. It's the one that is multiplied by the x. It can be written as b plus ax. It doesn't really matter the order because 5 plus 4 and 4 plus 5 are the same thing. So do not be tricked into thinking that the slope is always the first number in the equation. The slope is the number that is multiplied by the x. The y-intercept is the number that's off by itself, not being multiplied by anything at all. And so then we go one step further and say what are slope and y-intercept. Slope is often thought of as rise of a run, or change in y divided by change in x. Whereas the y-intercept is the value of y when it crosses the axis there at x equals 0. So that's your quick little algebra review. The next section is titled scatter plots. These scatter plots is kind of just a fancy way of saying a graph that, again, you would have seen in algebra class, where you just have a bunch of points on a two-dimensional graph. Every single point is an individual in the data set. Notice, of course, when I say individual, I don't necessarily mean person. It could be an individual car, or an individual animal, or an individual tree, or an individual place. Okay, it's that there's an x value and a y value. Again, note they are both quantitative values, not qualitative. So it's not just that it's numeric, but it's numeric values that have meaning. We can multiply, we can subtract, things of that nature, and we'd have meaning. And each x and y quantitative variable come from the same person for that point. So each point, the point 3, 6, that means whatever the x variable is measured as 3 for that person, place, or thing, and then it's the y value is measured as 6 for that person, place, or thing. Go to the next point, same thing. You've got another x value, another y value, and that's the x and y value for that same individual. Again, individual, thing, person, city, doesn't really matter. When we use the word correlation, we just mean relationship, association between two variables. Those are all kind of synonymous terms. If you recall, when we talked about distributions, we always said there were 3 things that we needed to assess with any distribution, right? Shape, center, spread. You've heard that said a lot. When we talk about correlation, there are 3 things that need to be talked about. There are 3 different things, but just like with distribution, you always should have been thinking to yourself, okay, there's 3 things that I can talk about, shape, center, spread. With correlation, there are 3 things we can talk about. The first is the form. which means what does it look like? Is it a straight line? Is it a curved line? Is it a wavy line? What exactly do the points do? And again, we're thinking about a scatter plot, so you don't have a picture in front of you on this page, but again, just think about the type of plot that you're familiar with from algebra where you have an x-axis, y-axis, and a bunch of points. The form is just what are the points doing, right? Are they all along a line, or are they all along a curve, or are they not? Right, so form just means what do we look like? In this course, we're going to focus in on linear associations. That doesn't mean that more complicated patterns don't exist, and we will see some other ones. And so you kind of just need to be able to say linear or not linear. We're not going to dive too deep in the rabbit hole of the not linear ones. So we're focusing on linear relationships. Second thing that we're thinking about is the direction of the association, and that is positive or negative. It basically just means if you look at the picture and you read it from left to right, are the points going up or down? Positive association means as you go left to right, as the x values get bigger, then the y values get bigger. So that's a positive association because as one thing happens to the x values, the same thing happens to the y values. A negative association is going to be when you look at the picture left to right and the points fall, they get smaller. It's a negative association because as the x values get bigger, the y values then get smaller. The opposite thing happens to them. And the last one that we're going to talk about is the strength of the relationship. And the strength says how close the points follow this relationship that we've been talking about. It means are the points close together or not? And so an example, if we have a golfer who wants to see what the relationship is between how fast he can swing a club and the distance the ball travels, we take a bunch of shots, we measure the club speed, and we see how far the ball goes. So this is an example of a scatter plot. Notice we don't have negative values for the x-axis. We don't have negative values for the y-axis. So it doesn't have to be your old school plot with 4 quadrants. It can just be the points of interest. It doesn't really matter. The idea is that we're just zooming in on whatever part matters. And again, each point is an individual thing. In this case, it's an individual swing of the golf club where we've measured on that swing both how fast the person swung the club and how far the ball went. And so when we talk about the 3 things that we're interested in assessing correlation, we say form, direction, and strength. So we can make sure you remember that form, direction, and strength. The form of this, as we talked about, we're kind of assessing just linear versus not linear. We can say some fancier not linear words if we want to, but for the most part, we're thinking linear, not linear. And I'd say that looks relatively linear. The points are going in a reasonable line. Then we talked about direction. It's positive because as I read this left to right, the points, the x values are going up, the y values are going up. The points are increasing as I look at it left to right, so that'd be positive association. And then the strength is how close the points are to this relationship. And I would say that's fairly strong because if I were to draw a line that kind of goes through, and I'm using goes through in air quotes, those points are all relatively close to that line as opposed to the point still going in the upward direction but being further apart. The idea being, if you can see my pointer here, the line that would exist between these points, the points aren't very far from that line, as opposed to if some of these points were further up here or the points they were further in here and it's spread further apart. Okay, so I would say this is a relatively linear pattern that is positive and relatively strong. And that's what I want us to be able to do here on this example. We want to evaluate the strength and direction of these relationships. And so if you want to kind of try to see if you can do this yourself, you can go for it. I think it's pretty straightforward which ones are negative and positive. Then we just have to think about strong, moderate, weak. Again, strong means all the points are really close together. Weak means the points are not. So if we think about the positive points, B is positive and looks very strong. F is positive as well as I. I looks weaker than F, so I would say I, F, and B are the positive ones, where I is the weakest, B is the strongest. We look at the negative. A, D, and G are all negative. The strongest one of those looks to be D. The weakest one of those probably looks to be A. might be tougher for you to distinguish between some of these. Notice in my weakest one, A, notice I have, say, a point here. This point would not follow the trend very well. So A is a little bit weaker because you have some of these points that are a little bit further away, whereas D does not seem to have any points at all that stray. G has maybe a point or two that strays a little bit further, but nothing quite like A, where some of these points are really straying out. So that's how I would assess those plots. Talk about next the sample linear correlation coefficient. This is going to be a numerical way to assess what we just did. Every time we deal with a correlation problem, we're going to both look at the plot to assess what the shape, strength, and direction are of that correlation. Just like we did looking at those previous ones. We said all of those looked relatively linear. We could address if they were kind of strong, moderate, weak, and we could address if they were positive, negative. So we could answer all three of those questions just using our eyeballs, just looking at it. And that's a very powerful thing to do, but sometimes we want a more mathematical approach rather than just a looking at it approach. And that's what the correlation coefficient does, is it calculates a number between -1 and 1 that tells us the strength between the x and y values in a sample, and it is denoted by the letter lowercase r. So anytime we have a sample of values that are paired quantitative values, we can plot them, we can look at them and assess the three key pieces of information we want to look at with regards to what is their relationship, but we can also come up with a mathematical number that tells us what we think about the relationship. Anytime those values come from a population and not a sample, we denote that by the Greek letter rho, just like you are rowing a boat. It looks kind of like a P, but that is the Greek letter rho, R-H-O. And some notes about R. It is not the only way to measure correlation, but it is the most common. So again, just as we talked about, we're measuring correlation. We are trying to see what the form of the relationship is, what the strength of the relationship is, what the direction of the relationship is. We can do that using our eyes, or we can do that using R. The sign of the correlation indicates the direction of the relationship. That's helpful because remember we said that's one of the three key pieces of information. We wanted to know the direction of the relationship. The sign tells you that. A positive correlation indicates that the two variables tend to increase together. As x gets bigger, y gets bigger. But a negative correlation indicates that as one variable increases, the other is likely to decrease. As my x gets bigger, my y gets smaller. So key thing number one, anytime we get R, the sign tells us the direction. So negative values have negative correlation, positive values have positive correlation. The magnitude of the correlation indicates the strength of the relationship. And maybe more specifically, the absolute value of the magnitude. We said that R falls between -1 and 1. It might be helpful, it's likely going to be helpful for you to think of the sign as something completely different from the number that follows it. So make sure you hear that. Okay, the sign is completely independent of the number. The sign just tells you the direction. The number, the magnitude, tells me the strength. So I want to view a correlation of -0.6 and +0.6 as the exact same, with the exception that one of those is going to be points going up and one going to be points going down. Okay, so the negative, maybe don't think of it like a number line. Okay, think of the negative as it's attached, but it's its own separate piece that tells me that direction, whereas the magnitude tells me the strength. And larger numbers mean a stronger relationship. So the closer we get to 1 or -1, the stronger the relationship. Again, this is a concept that a lot of people kind of struggle with. So what does it mean? It means the points are closer to each other. They're closer to that hypothetical line that would go through them. Smaller numbers, when the numbers get closer to 0.2, 0.1, closer to 0, or negative 0.2, because again, the negative doesn't really matter. The negative just tells me the direction. When you get those points that fall down closer to 0, that means the points are further away from each other. So when we talked about strong, weak, moderate previously, the stronger correlations are up in the 0.7, 0.8, 0.9 range. The weaker ones are in the 0.1, 0.2, 0.3 range. The moderate ones, maybe 0.4, 0.5, 0.6. So we already mentioned R is always between -1 and 1. And if you land at either one of those values, that means you have a perfect relationship and all of the points fall on the same straight line. So we talked about the magnitude tells you how close the points are to this line. If you actually do hit 1, it's so strong, it's perfect, and all the points fall on the line. If you have a correlation of 0.99, it would mean that the points almost all fall in the same straight line. There's just a tiny bit of error there. There's a tiny bit, a little bit off, but almost right on that line. And then again, the further away you get from 1, then the further the points would be from that line, all the way down until 0, which indicates that there's no linear relationship between the variables. And so we've talked about 2 of the 3 key components that we want to assess with these associations. We've talked about the direction, we've talked about the strength, we haven't talked about the form, but I hope that you've seen it in what you've written in, especially these last 2 bullet points. R only measures the linear relationship. Okay, so anytime you're using R, you are measuring specifically the linear relationship. And if you look at the top of the page, you'll confirm that, right? When you wrote down what R was, you wrote down a number between -1 and 1 that measures the strength of the linear correlation. So if we have a different form, R is not an appropriate measure to use because R can only measure the linear correlation. So that kind of wraps us up with all 3 pieces. When we're talking about R, we are measuring only the linear correlation. The sign tells you the direction, and then the magnitude tells you the strength. The bigger the number, the closer it is to 1 or -1, then the stronger that relationship is. The closer it is to 0, the weaker it is. Then our last bullet here, yes, it's in all caps. Yes, I'm yelling it at you. Correlation does not imply causation. That's a very important key point to note. We talked about this a little bit at the very start. 2 variables that are correlated does not mean that one caused the other. And that's a key thing that I need you to leave this course with, is that anytime you see a relationship between 2 variables, and this is just from an English standpoint, just let's break this down from the English words. Anytime you see 2 variables have a relationship with each other, it does not necessarily mean that one caused the other. It doesn't mean it didn't either, right? Think about what the word imply means. It's just saying it doesn't imply. It doesn't mean it doesn't either, right? If A and B are related via correlation, maybe A caused B, but maybe it didn't. We don't know. When we do correlation analysis, when you say 2 variables are related to each other, that's all you can say, is that as one goes up, the other goes up. But that doesn't mean that one caused the other. It doesn't mean it didn't either, right? I just need you to understand what we're saying, what we're not saying. That's going to be a common theme here in this chapter, is understanding what we're saying, what we're not saying. When we say 2 variables are correlated, we are saying that as one goes up, the other goes either up or down, depending on if it's positive or negative. What we are not saying is that we can conclude one caused the other one. The only way to determine causation from a statistical standpoint is by doing controlled experiments. We talked about experiments way back in chapter 1. That's where we have a control group. We apply some treatment to one group. We have a very similar looking group for the other side and don't apply the treatment to that group. And then we see are there any differences between the two groups. That's the way to determine causation. It is not a correlation analysis, because 2 things are correlated. Maybe one caused the other, maybe not.